When you've completed this lesson, you should be able to recognize parallel and perpendicular lines and understand their properties. In addition, you'll be able to measure angles. And you'll find unknown angle measures in triangles algebraically. The photonics technicians use geometry very often, involving parallel and perpendicular lines. Photonics technicians measure the angles between those lines in the beams that are not parallel. When angles can't be measured, the properties of the triangles can often be used to deduce the angles. For example, you have Brewster's angle for reflection for producing polarized light. Or you have Snell's law of refraction for tracing rays that pass through an interface of different media. All of those will involve determining and measuring angles. Here's an example scenario that you might encounter as a photonics technician. Laser cavities use Brewster's windows to achieve polarization of the laser beam. The drawing shows an unpolarized incident ray striking the window, undergoing both reflection and refraction. And the same thing at the exit media, reflection and refraction. So we're asked to find angle A1 if it's to be Brewster's angle, angle A2 for the reflected ray, angles B1 and B2 and B3, and angle B4. Phew, that's a lot of calculations, lots of angles and lots of geometry, and you'll be able to do all of it by the time you finish this module. So hang on to your seats and let's return to this after we review some of the skills necessary to solve this kind of problem. First, let's review some of the terms and definitions pertaining to lines. Parallel lines are two or more lines that never intersect on a plane. These line segments are all parallel. Perpendicular lines meet at a 90-degree angle, and we say they form a right angle is the term that you'll often hear, or that they're square angles. Notice that the symbol used looks like a little square. If you get two of them back to back, it looks like a little step. A ray is a line segment that has an arrow on it, meaning that it keeps on going forever and ever. And it's got an end point. And that end point is useful because if you put another ray starting at that same end point, you form an angle. And we want to be able to measure those angles. We measure angles using degrees. There's 360 degrees in a circle. And just like there are 60 minutes in a clock hour, well, then each of those minutes must have 6 degrees in it, just to give you an idea of how big a degree is. We will refer to special groups or classes of angles. For example, the acute angle is greater than 0 but less than 90. A right angle, as you've already heard, equals 90 degrees. An obtuse angle is greater than 90 degrees but less than 180. And of course, you know what 180 degree is. That's a straight angle. Let's look at example 1 of measuring angles. How would you measure angles? We're going to measure an angle with a protractor. So let me show you how to use a protractor. You align the midpoint mark of the protractor with the vertex of the angle, right there. Now your protractor may have some more plastic down at the bottom part of it there, but I've just drawn this one here without that so that it makes it easier to line things up. But you'll align the midpoint mark of the protractor with the vertex of the angle, or the end point where the two rays join together. You align AB with the 0-degree line of the protractor. So be real careful to get both the point on the 0 and the end point on the center of the protractor lined up perfectly. Then you're able to read the measures of the angle appear on the protractor. Protractors will often have double sets of numbers, and so you'll have to realize that we're starting off at 0 degrees, going 10, 20, 30, 40, 50, and 60 to get up to here. So don't let the other numbers confuse you. That would be for measuring an angle that came all the way from over here. That would be 120 if it came all the way from over here. So in our case, angle CAB is equal to 60 degrees. And you'll notice that we refer to the angle by these endpoints that are used to construct the angles. Here's the one where we'll draw an angle using a protractor. So we're given ray IJ, and we're asked to draw an angle JIK. So we need to find a point K out here that will produce a 120 degrees angle. So again, we'll align the midpoint just like before and line up the line right on the 0 degree line here. So now if we wanted to draw a 10 degree angle, we would have the line coming off here. If we wanted to draw a 60 degree angle, the line would come up this way. What we need is a 120 degree angle. So we need to come all the way over to 120 and put that dot right there and label that point K. Now we're ready to draw a straight line that joins I to K, and you can use the edge of your protractor to do that. And now we've got it. There's angle JIK, 120 degrees. Triangles are going to be very helpful in geometry in ascertaining different angles, because we know that a triangle has 3 sides, and we know that it has 3 vertices. Here we'll label them A, B, and C. And there's 3 angles inside that triangle: angle A, angle B, and angle C. And you see how they correspond to the vertices. In every triangle, the sum of the measure of all of those angles always equals 180 degrees. That's a very important fact for you to remember. The sum of the angles in a triangle always equal 180 degrees. So let's look at example 3 that asks us to solve for the angle in triangle ABC if we know that angle A is 105 degrees and angle C is 48 degrees. So how can we find the measure of angle B? We know that the sum of those angles must equal 180 degrees. That's what you just learned above. And so we'll say 105 degrees plus angle B, whatever that is, plus 48 degrees have to all equal 180. So all we have to do now is the algebra to solve for angle B, which you know means we'll take 180 minus 48 minus 105 degrees equals 27 degrees. Now there's some important terminology that you may encounter in your study with triangles. For example, we have equilateral triangles that have 3 congruent sides. We show congruence many times by just putting a tick mark on the equal sides. We have isosceles triangles, which have 2 congruent sides. And we've got scalene triangles that have no congruent sides. Every side is a different length. The measures of the angles in the triangle is another way to describe triangles. We have equiangular triangles, which have 3 congruent angles. We have right triangle that has a 90-degree angle in it. Those are very common and very useful, and you'll use those immediately here in the course in just a minute. We have acute triangles, where all the angles in the triangle are less than 90. And we have obtuse triangles, where one of the angles is greater than 90. Now, those terms aren't really so important that you can't exist without them, but if somebody mentions to you that you have an acute triangle, now you'll know what it is. Example 4 asks you to build a toolbox using some geometry. So we've got a toolbox here with a rectangular compartment in the middle of it, probably to put some smaller tools or something, and a divider going across the diagonal between B and D on this drawing. And we're asked, what will be the measure of angle X and of angle Y? And you'll notice that we are given one angle is 35 degrees. And how are angle X and angle Y related? Well, first of all, the corners of a rectangle always form 90 degrees. And so you'll see we've got 2 right triangles here. The sum of the angles in each of those triangles equals, 180 degrees. So in triangle BCD, we'll have 35 degrees plus the 90 degrees plus x equals 180, just like we saw in the previous example. So we can solve for x, and we'll find that x equals 55 degrees. So the diagonal makes an angle of 55 degrees with side BC, the short side. So now we're trying to find angle y. Okay. Since angle CDA in this corner is 90, correct? Is that a right angle? If it's a rectangle, all of the corners in here are right angles with the sides. So we know that 35 plus y is going to equal 90 degrees, and we can solve for y and find that y is going to be 55 degrees. And what is the relationship between angle x and angle y? Well, look at that. They both turned out to be 55 degrees. So there's something you learned about diagonals in a rectangle. What do you think about angle z? Would you like to venture a guess? I'll bet you already know the answer without even doing any math. It's going to be the same as this angle over here, so it will be 35 degrees. Very good. You're learning them fast. Now we're ready, I think, just with all that, to look at our opening scenario. We're asked to find the angle A1 if it's going to be a Brewster's angle, such that the tangent of B1 equals n, the index of refraction in our glass. So we've got n is equal to 1.5 in our glass. We've got angle A1 coming in here. It's going to reflect and refract. For angle A1 to be a Brewster's angle, then the tangent of A1 is going to have to equal n, 1.5. Now you may not have encountered the tangent function before. We'll look at that in the next module, but you can still use it on your calculator. Right? The tangent of A1 is equal to 1.5. So if we take the inverse tangent of both sides, that will give us A1. The inverse tangent function of the tangent function will give us A1. So if we take the tangent inverse of both sides, and we have the tangent inverse then of 1.5 is equal to A1. If you use your inverse tangent function, or the tan to the minus 1 power as it looks like on your keys, then you'll get 56.3 degrees. Little caution here, be sure to put your calculator in degrees mode. Some advanced calculators can be in radians or degrees, and you'll need to be sure that you're in degrees mode. And one way to find out is if you don't get 56.3 degrees for doing this problem, then you're probably in radians mode. Okay, part B of this problem says, what is that angle A2 for the refracted ray? If A1 comes in at the Brewster's angle, what is going to be the angle for A2? Well, in general, the angle of reflection measured with the normal always equals the angle of incidence measured with the normal. And this is the normal. This is a line, imaginary line we draw that is perpendicular to the surface of the media. Perpendicular means what? It means 90 degrees. So if angle A1 is coming in and angle A2 is the angle of reflection, and those are equal, then it's pretty obvious that A2 is going to equal the Brewster's angle that we just calculated in part A of this problem, 56.3 degrees. Part C says, find the angle of refraction. All right? The angle of refraction is also measured against the normal. And so we've got angle A1 coming in and angle B1 coming out of the interface of that media, measured against the normal line. So we'll substitute our variables into Snell's law, which says n1 sine theta equals n2 sine theta 2. And here in our case, we've got n1 is the index of refraction of the media outside, which we'll presume is the air, the index of refraction of 1. And N2 is the index of refraction of the media that we're going into, which is 1.5. And angle A1 is the angle of incidence in the air, And angle B1 is the angle of refraction inside the media, or in this case, our glass. So we need to isolate that term with the B1 in it. So we need, since it's multiplied by N2, we're going to divide both sides by N2. And sine of B1 will equal N1 sine of A1 divided by N2, which we can now plug those variables in and calculate. We'll take the inverse sine of both sides. Since we don't want sine of B1, we want B1, just like we took the inverse tangent. Now we'll take the inverse sine. And the inverse sine of 0.5546 is about 33.7 degrees. So the ray is refracted inside the glass at about 34 degrees from the normal. Next part asks you to find the angles B2 and B3. B2 and B3 are the angle of incidence on that second interface, and B3 is the angle of reflection from that. And you notice they're both with reference to a new surface normal that we're looking at now. Not the old one, but this new one. Look at B2, and you'll notice that B2 is part of a right angle formed by the normal and the glass surface. B2 is part of that angle. The other part of that angle is angle QRP. Well, QRP just happens to be part of a triangle formed by QRP. We've seen that triangle, and it's got angle B1 in there that we just measured. We just determined B1 to be 33.7 degrees. So now, if this is a right triangle, and we know B1, and we know this is 90 degrees, then we can calculate the third angle, QRP. That'll be 180 minus 90 minus 33.7 equals 56.3 degrees. So angle QRP is 56.3 degrees. All right, so now if we know angle QRP, we should be able to calculate B2, because B2 is equal to 90 minus QRP, or in this case, 33.7 degrees. As before, we can quickly identify the angle for B3 because this is a reflection, just like we saw up here. So we have a reflection down here, and we learned that the angle of reflection equals the angle of incidence. So in this case, B3 equals B2, which is also equal to 33.7 degrees. And thus we can note, interestingly enough, that angle B3 equals B2 equals B1 equals 33.7 degrees. So all our labeled angles inside there equal 33.7 degrees. Find the angle, finally, of refraction for B4, the outside. When the ray leaves the glass, what angle does it make with the normal? To do that, we'll once again use Snell's law that defines what happens between the interface between two different media with two different indices of refraction. In this case, N1 will be the glass, which will be 1.5. N2 will be the air, which we've said is 1.0. The first angle will be the angle of incidence at the interface, which will be B2. And the exit angle will be angle theta 2, or B4. And of course, we want to solve for B4. So here's Snell's law with our variables plugged in. We need to isolate that term with B4. Since it's multiplied by N2, we'll again divide both sides by N2, which will leave sine of B4 on this side, and N1 sine of B2 divided by N sub 2 on the right side. And we can substitute our values for N1 and N2 and our angle for B2, and we'll determine that the sine of B4 is equal to 0.8323. If we take the sine inverse of both sides, then B4 will equal the sine inverse of 0.8323. Again, using your calculator, with the inverse sine function, you can find that B4 is equal to, oh, there's a number we've seen before, 56.3 degrees. At exactly the same as Brewster's angle. Isn't that interesting? So the angle of incidence of the ray over on this side is the same as the angle that the ray exits on this side. It's just been shifted down a little bit by the refraction that occurs inside the window. It's time to look at some practice exercises for this module that'll build up your confidence that you can actually do these kinds of geometry problems. First of all, let's answer the questions about this drawing here. If angle 1 is equal to 90 degrees, what can you say about those two lines L and M? Well, the lines meet at 90 degrees, so lines L and M are perpendicular. And we sometimes use this symbol here to indicate L is perpendicular to M. So if P is perpendicular to L, what would be the measure of angle 2? Well, again, you apply the definition of perpendicularity. That means angle 2 must be 90 degrees if P is perpendicular to L. And if angle 1 is 90, well, what is the measure of angle 3? Do you remember that terminology we had about straight angles? That's a straight angle right there. We know that must be 180 degrees. And so 1 plus 3 must equal 180, and we can solve for 3 since we know what angle 1 is, and that would make it 90 degrees. If angle 1 were 90 degrees, what can you say about the measure of angle 4? There's a couple ways to answer this. One of them is if we know that angle 1 and angle 3 form a straight angle with line M making angle 3 90 degrees, well then so too 3 and 4 must form a straight angle, and we can just say that angle 4 must be 180 minus angle 3, and thereby angle 4 must be 90 degrees. Another interesting fact not covered in the text is that when you have two rays crossing each other like this, or two lines, these opposite angles are always equal. Angle 1 and angle 4 are always equal. And angle 3 and this angle that's not labeled over here are also equal. So even if these lines were not perpendicular, you could still say that if you knew angle 1, you would also be able to know angle 4 because it would be equal to angle 1. And there is one more part to this. It says, what can you say about lines M and P, these two distant lines here? Both lines M and P are perpendicular to the same line, and that just happens to make lines M and P parallel. And there again is the symbol that you'll often see to indicate M is parallel to P. All right, here's exercise 2, a little bit more real world kind of problem. See if you can complete the statements about the sketch here. The drive shaft is blank to the rear axle. What does that mean? What is the relationship between the drive shaft and the rear axle shown in the drawing? Why, it's perpendicular, right? I heard you. Yes, that was easy. How about the next one? The rear axle and the front axle are what? How are they compared to each other? You probably figured it out by now. They are parallel. Very good. This one's a little harder. The drive shaft is what to the direction of travel? Well, it's also parallel. You thought there was a new one coming. This is parallel too. And now here's one that we did not cover in the text, but we're going to see if you know it. When the tires on the car have spun around 360 degrees, that is one revolution, the distance they have moved on their ground is about the same as their circumference. That's simply the definition of the circumference, is the distance all the way around the circle. And of course, as the tire rolls on the ground, it will actually trace out the circumference of that circle onto the ground. Exercise 3 asks you to solve for x in some triangles where we've given you a couple angles. So you know that the sum of the angles in the triangle equals 180 degrees. So this should be pretty straightforward. You've seen this in this unit. So x plus 114 plus 39 degrees equals 180. You solve for x, you would subtract 114 and 39 from both sides, leaving x equals 27. And what kind of triangle is that? Is that a obtuse triangle or an acute triangle or what? Right, it's an obtuse triangle because it's got one angle that's greater than 90 degrees in it. Now note the straight angle in this triangle so that you can identify that the missing angle here must be 60 degrees, right? So 180 minus 120 is 60 degrees. So now you can solve for x Just like before, x plus 60 plus 67 must equal 180, and x is equal then to 53 degrees. And that concludes our treatment of Module 8, Geometry. I know you're going to have a lot of fun working with angles and parallel lines and perpendicular lines and triangles. It's a fun thing to do, and you'll encounter a lot of geometry in your photonics career. So study up and learn this stuff really well, and we'll see you next time.